Dear students, today we will discuss about the Fourier transform for the application of principal communication engineering. So this topic is the basically mathematical topics, and there are many formula and many derivations for the Fourier transform. So we will discuss about the here complex numbers. So what is the complex number? So suppose x equal to a plus jb, where j equal to under root minus 1. If we want to addition two complex number, so we can write this a plus jb and plus c plus jd equal to a plus c plus j b plus d. So real part, and there is the two parts. First part is the real parts and second part is the imaginary part. So a plus c here is the real part, and j b plus d, that is the imaginary parts of the complex numbers. And next we can multiply these two complex numbers. So we can write these two numbers in the form of multiplication. So a plus jb multiplied c plus jd. So what is the result of these two complex number after the multiplication? That will be equal to ac minus bd. That is the real part, and jad plus bc. That is the imaginary parts of the complex numbers in the multiplication function. And what is the magnitude of the complex number? So x equal to 1 plus jb. So what is the magnitude of x? X magnitude equal to under root a square plus b square, and the phase will be phi x equal to tan inverse b upon a. And also magnitude, phase magnitude notation here, x equal to magnitude of x into e to the power j phi x. So in this figure, there is a imaginary parts we take on y-axis, and real parts we take on x-axis. So resultant magnitude is the under root a square plus b square of the complex number a plus jb. Multiplication using magnitude phase representation here. So what is the multiplication of function xy equal to magnitude of x into e to the power j phi x into magnitude of y into e to the power j phi y, and equal to magnitude of x and magnitude of y into e to the power j into phi x plus phi y. So this is the multiplication using the magnitude phase representation. Next one is the complex conjugates. So we can write x star, that is the complex conjugate of x, that will be a minus jb. Suppose x equal to a plus jb, then complex conjugate of x star equal to a minus jb. And there is some property of the this complex number. So magnitude of x equal to magnitude of star x. So phi x star equal to minus phi x star. So x into x star equal to x magnitude whole square. So this is the property of the complex number a plus jb. So here is the formula of Euler's formula. So e to the power plus minus j theta will be equal to cos theta plus minus j sin theta. So this is the Euler's formula. And what is the magnitude of this function? Then e to the power plus minus j theta magnitude equal to under root of cos square theta plus sin square theta, and this will be equal to 1. And also, what is the phase shift? So phi e to the power plus minus j theta equal to tan inverse plus minus sin theta upon cos theta and equal to tan inverse plus minus tan theta and equal to plus minus theta. So this is the phase shift of this Euler's formula. And what is the properties? So properties, first property is that sin theta equal to 1 upon 2j into e to the power j theta minus e to the power minus j theta. And also, what is the cos theta? Here, so cos theta equal to 1 upon 2 into e to the power j theta plus e to the power minus j theta. So these are two properties, first for sin theta and second for cos theta. And what is the sine and cosine functions? So periodic functions generally form of a sine and cosine functions. So here yt equal to a sine into a into t plus b, and also yt equal to a cos a into t plus b. So amplitude of a, so and here what is the period? 2 pi upon amplitude of a, and phase shift is the here in this b. B is the phase shift and a is the amplitude and period is the 2 pi upon magnitude of a in this general form of sine and cosine functions. These are the sine and cosine functions waveform. First waveform show the sine function waveform, and second show the in this figure cosine function waveforms. So there is the 90-degree phase shift between sine and cosine function waveforms here. Now, next one is shifting or translating the sine function by a constant v. So in these different waveforms, first show the waveform y equal to sine t, and second show the y equal to sine t plus b. So there is the shifting of a constant b. Here v is greater than 0, and also in waveform c y equal to sine t plus b. So there is a also shifting of constant b, what here v is less than 0. So note here cosine is a shifted sine function, and we can shift a cos function into sine functions. So cos t equal to sine t plus pi by 2. So this is the cosine shifted to a sine function by this formula, or by this shifting a phase shift pi by 2, pi by 2. Here phase shifting is the pi by 2. Now changing the amplitude a of the any sine or cosine functions waveform. So here y equal to 3 sine t. So here amplitude of the this sine wave is the 3. So this is the waveform is the have the amplitude of 3. And we also changing the period in the waveform. So here we change the period t equal to 2 pi upon amplitude of alpha. So consider a equal to 1 and v equal to 0 and y equal to cos alpha t. So in this waveform, show the changing the period t equal to 2 pi upon magnitude of a. Next transformation is the image transform. So in image transform, many times image processing tasks are best performed in a domain other than the spatial domain. So here key steps are, so first in the transform the image, second one is the carry the task in the transport domain, and third one is the apply inverse transform to return to the spatial domains. So in this block diagram, there is the spatial domain function xy, and this function is transformed into tuv, and next one is the operation r. The output of r is the r into t to uv. So next one is the inverse transform of this input signal, and output signal of inverse transform network is the gxy. This is the spatial domain, and so this is the image transform of any functions. Next one is the transformation kernels. So here is the two transformation. First one is the forward transformation, and second one is the inverse transformation. So in forward transformation TUV, that is the T function, equal to summation of first summation of x equal to 0 to n minus 1, and second summation is the y equal to 0 to n minus 1 into fxy into rxy and here u equal to 0, 1 and so on n minus 1, and value of v equal to 0, 1, 2 and n minus 1. So this is the forward transformation. Second one is the inverse transformation of so inverse transformation fxy equal to summation of u equal to 0 to n minus 1 and v equal to 0 to n minus 1 tuv into s xy uv, where x equal to 0, 1 and n minus 1 and y equal to 0, 1, 2 and so on n minus 1. So these are the two transformation of kernels. So what is the property of kernels? So there are some properties of kernel here. A kernel is said to be separable if function r x y uv equal to r1 x uv into r2 y uv. So kernel is said to be separable if this condition is satisfied. Second, a kernel is said to be symmetric if function r x y uv equal to r1 into x u into r1 y v. So a kernel is said to be symmetric if this condition is satisfied. So these are the two kernel property. So there are some notations for the different Fourier transform. So first one is the continuous Fourier transform FT, and second one is the discrete Fourier transform DFT, and third one is the fast Fourier transform FFT. So there is the total three Fourier transform: Fourier transform FT, discrete Fourier transform DFT, and fast Fourier transform FFT. Next one is the Fourier series theorem. So what is the theorem for the Fourier series? So theorem for Fourier series say any periodic function can be expressed as a weighted sum infinite of sine and cosine function of varying frequency. So this is the statement of Fourier series theorem. We can write this theorem in the form of mathematical. So Ft equal to A naught plus summation from n equal to 1 to infinite A n cos n F naught t plus summation n equal to 1 to infinite Bn sin F n F naught t. So F naught is the here fundamental frequency. So this is the mathematical representation of the Fourier series theorem. There are different waveforms in these figures, waveform figures. So first waveform is the have the frequency f1. So this is the cos waveform, cos f1t. Second waveform is have the frequency f2. So this is also cos waveform which have the frequency f2. And second one is the also cos waveform which have the frequency f3. So these three cosine waveforms are adding, and after the addition we find the total function ft as shown in this next second waveforms. So first Fourier transform is the continuous Fourier transform ft. So we will discuss about the ft transform. In continuous Fourier transform ft, transform a signal or a function from the spatial domain to the frequency domain. So forward Fourier transform f, capital F of the fx equal to fu equal to minus infinity to infinity integration of minus infinity to infinity fx into e to the power minus j 2 pi ux dx, and inverse Fourier transform of this Fourier transform fd f inverse of fu equal to fx equal to integration from minus infinity to infinity f u into e to the power j 2 pi ux du. So this is the inverse Fourier transform, and where e to the power plus minus j theta equal to cos theta plus minus j sin theta. So why is ft useful? So first one is the easier to remove undesirable frequency from the FT Fourier transform. Second is the faster perform certain operation in the frequency domain than in the spatial domain. So due to these two regions, FET is useful in the Fourier transform. There are some examples of removing undesirable frequencies. So first signal or waveform show the noisy signal of, and so second signal show the frequency, individual frequency terms, and first one show the sum frequency terms, and third one waveform show the filter frequency term, remove high frequencies, and fourth one waveform is the new sum image, here reconstructed signals. So there are some examples in which we removing the undesirable frequencies from these signals. Next, how do frequencies show up in an image? So low frequencies correspond to slowly varying information, for example, continuous surface. And second one is high frequencies correspond to quickly varying information, for example, edges. So this is the example in which noise reduction by using the Fourier transform. So in first picture there is not clear due to the noise, but the last picture is removed and reduction of the noise by the using of FT. So this picture is clear as compared to first picture. So this is the application of FT in noise reduction. Next one is the frequency filtering steps. So first step is that take the FT of fx. So Fourier transform of fx is the f into small fx. Second one is remove undesirable frequency. So here d into f into fx. And third one is the convert back to a signal. So we convert back to a signal by the inverse transform. So fx equal to f inverse d into fx. So we will talk more about this in next topics. There are some definitions of Fourier transform. So fu is a complex number. So we can write this fu equal to ru plus jiu, where r is the imaginary part and iu is the ru is the real part and iu is the imaginary part. And next one is the magnitude of ft spectrum. So magnitude of the ft spectrum equal to under root r square u plus I square u, and phase of the ft. So phase of fu equal to tan inverse iu upon ru. Next one is the magnitude phase representation. So magnitude phase representation fu equal to magnitude of fu into e to the power j high u. And next one is power of fx pu equal to magnitude of fu ka whole square equal to r square u plus I square u. So these are the some definitions of the Fourier transform. There is a two examples of first one is the rectangular pulse and second one is the sine function. So we can represent the rectangular function as figure 1 and sine function by figure 2. Next one example is impulse function of delta functions. So definition of delta function. So delta x equal to limit of x tend to 0, 1 upon a rectangular into x upon a. So this is the delta function. And this function have the property integration of minus infinity to infinity delta x ds equal to 1 and also integration of minus infinity to infinity plus infinity fx delta x minus x naught dx equal to fx naught. So this is the property of delta functions. So ft of delta function, what is the Fourier transform of delta function? So Fourier transform of delta function equal to integration of minus infinity to plus infinity delta x e to the power minus j 2 pi ux into dx equal to e to the power 0 of equal to 1. So Fourier transform of delta function equal to 1 will be 1. There are also some examples for spatial and frequency shifting. So function fx tends to fu, then first fx minus x naught tends to e to the power minus j 2 pi ux fu and delta x minus x naught tends to e to the power minus j 2 pi ux into fu. So second one is the fx e to the power minus plus j 2 pi u naught x tends to f u minus u naught and also e to the power j 2 pi u naught x tends to delta u minus u naught. So these are the frequency shifting examples. And these are the examples of sine and cosine function. So Fourier transform of cosine function cos 2 pi u naught x equal to 1 by 2 into delta u minus u naught plus u plus u naught. So that is the example of sine and cosine. And this also is represented in these two figures, first and second. First one is the cosine function and second one is the transfer and Fourier transform of this cosine functions. And that is the Fourier transform of the sine function. So Fourier transform of sine function sine 2 pi f naught x equal to j upon 2 into delta u plus u naught minus delta u minus u naught. So this is the Fourier transform of the sine function, and this is also represented by in the graphical representation. First, figure show the sine function, and second figure show the Fourier transform of this sine functions. Next one, extending Fourier transform in 2D. So double differentiation, or first forward f Fourier transform of function f xy equal to f u v equal to double integration from minus infinity to plus infinity f xy e to the power minus j 2 pi into ux plus vy into dx plus dy, and that is the forward Fourier transform of function fx. And second is the inverse Fourier transform of the function fxy. So inverse ft will be f uv equal to f xy equal to double integration from minus infinity to infinity f into uv e to the power j 2 pi ux plus uy into du dv. So this is the extending of the Fourier transform in the double differentiation. There are some examples of 2D rectangle functions here in this graphs and graphical representation. Next one is the DFT, discrete Fourier transform. So discrete Fourier transform fx equal to f x naught plus x delta x, where x equal to 0, 1, 2, and n minus 1. So this figure or graphical representation show the discrete Fourier transform, and discrete Fourier transform DFT have the forward DFT. So forward DFT fu equal to 1 upon n summation of x equal to 0 to n minus 1 fx into e to the power minus j 2 pi ux upon n, where u equal to 0, 1, 2, 3, and n minus 1. And the next one is the inverse discrete Fourier transform, inverse DFT. So fx equal to summation of u equal to 0 from n minus 1 fu into e to the power j 2 pi ux upon n, where x equal to 0, 1, 2, 3, and n minus 1. Fu is discrete, so fu equal to f into u del u, where u equal to 0, 1, 2, 3, 4, and n minus 1 also, and del u equal to 1 upon n del x. So these are the some examples of DFT here. Next, extending DFT to 2D double differentiation. Assume that fxy is m into n. So in that case, forward DFT f of fu v equal to 1 upon m n, double summation of x equal to 0 to n minus 1, and second v equal to 0 to n minus 1 fx y into e to the power minus j 2 pi ux upon m plus vy upon n, where u equal to 0, 1, and n minus 1, and v equal to 0, 1, and so on n minus 1. And next one is the inverse DFT. So inverse DFT fxy equal to double summation. First one is u equal to 0 to m minus 1, and second v equal to 0 n minus 1 f u v e to the power j 2 pi ux upon n plus u by upon n, where x equal to 0, 1, 2, 3 and m minus 1, and y equal to 0, 1, 2, 3 n minus 1. So this is the extending DFT to 2D. And there are some special cases here in which fxy is n into n. So these are the two examples. Of first one is the forward DFT and second one is the inverse DFT of xy, and first one is the forward DFT of fuv. Visualizing DFT, so typically we visualize f or amplitude of fuv. The dynamic range of amplitude UV is typically very large. Applying stretching, so these are the visualizing of the DFT in these figures. DFT have the some property. So first property is separability. So first property for forward DFT and second for inverse DFT and third for kernel is separable. And rewrite FUV as follow, and we find the FUV equal to 1 upon n integration of, sorry, summation of x equal to 0 from n minus 1 to the power minus j2 pi ux upon n into fxv. And next one is the how can we compute fxv. So nx dft of rho of fxy, how can we compute fuv? So fuv equal to 1 upon n summation of x equal to 0 to n minus 1 e to the power minus j 2 pi ux upon n into fxv. There are also some DFT properties here, and these figures show the DFT separability property. Second property is the periodicity. The DFT and its inverse are periodic with period n. So FUV equal to F U plus n into V equal to FUV plus n equal to F U plus n and V plus n. So this is the second property of the DFT, and also we can represent this by the graphical representation that is shown in these two figures. Third one property of the DFT is the symmetry. So if xy is real, then fuv equal to f star minus u minus v equal to magnitude of fuv equal to magnitude of f minus u minus v. So f xy real and even, then f uv real and even also. then fxy real and odd, then fuv imaginary and odd. So this is the symmetry property of the DFT. Third one is the, fourth one is the translation. That is the fourth property of the DFT. So here f x minus x naught, y minus y naught equal to fuv e to the power minus j 2 pi ux naught plus vy naught upon n. Translation is frequency domain fx y e to the power j 2 pi u naught x plus v naught y upon n tends to f u minus u naught v minus v naught. So here, to show a full period, we need to translate the origin of the transform at u equal to ny2 or ny2 in 2D case, ny2 ny2 in double differentiation case. And also to move fuv at ny2 takes u naught equal to v naught equal to ny2. So fxy minus 1 have the power x plus y equal to fu minus ny2 v minus ny2. These are the fourth property of the DFT rotation. So rotating fx by y theta rotate. So fuv by theta. So these graphs show the rotation property of the DFT. In these graphs, the function is rotating by the theta angles. Next property of the DFT is the addition and multiplication. So Fourier transform of addition fxy plus gxy equal to fxy plus fgxy. So we can write in addition of the Fourier transform in the property 6, and also second property is the multiplication. Seventh property of DFT is the scale. So AFXY equal to AFUB. So this is the scale property of DFT. And next one is the average value property, that is the number 8 property of the DFT. So average f average xy equal to 1 upon n squared, summation of x equal to 0 from n minus 1 and summation of y equal to 0 from n minus 1 fxy, and fuv at u equal to 0 and v equal to 0. So f average xy equal to 1 upon f00. Next one is the magnitude and phase of DFT. So what is more important? Use inverse DFT to reconstruct the image using magnitude or phase only transformation. So here reconstruction of the image using by the magnitude or phase only information. Reconstructed image using magnitude only. Magnitude determines the contribution of each component. So reconstructed image here using phase only. So phase determines which components are present. So in this figure A and a picture, and second figure B, phase angle, and picture C, a constructed using only the phase angle, and the picture D, the constructed picture using only the spectrum, and picture E, construction using the phase angle correspond to the uh, woman, and the spectrum corresponding to the rectangles, and D, the DF picture is the constructing using the phase of the rectangle and the spectrum of the movements. So these are the magnitude and phase of DFT. These are the some reference books for this topic. First one is the communication system by the Topsilin, and second one is the analog communication by Simon Jenkins. And there are some multi-choice questions here also to clear the concept of this topic. So thank you very much.